So, let us have a quick review on the topics that have been discussed so far in the context of Green's functions. So, the Green's function consists of time ordered product of a creation and an annihilation operator, followed by n interaction terms, which are all written at discrete times. That is the first point. So, this was just to say that it is of the form of a phi 0 and a t, and then a c k t and a c k prime t prime dagger, and then there are h primes or h interaction terms that are at t 1 and all the way up to h prime t n, and this is the expectation value of the time ordered product is taken. So, this is one annihilation term, and there is a creation term, and this thing equal to, so this along with a minus I is same as my g k, let us say that, let us make this same. So, it is a g k and t minus t prime. So, this is what it is proportional to, with a factor of minus I is, we will see all that in a short while. Now, each order of h prime included here in this expression will give a sort of that order of the Green's function. So, if I include one h prime, I will get a first order Green's function. If I include two h primes, I will get a second order Green's function, and so on. So, these are in principle we have infinite number of these h primes. So, a full Green's function contains infinite number of h primes. What are the implications of each of these h primes is what we are going to come next. So, a fully interacting Green's function contains a one creation and one annihilation and n of those h primes. So, each of the third point is each of the interaction terms h prime itself is a collection of two creation and two annihilation operators. This is what we have learned when we did second quantization, that each interaction term at least has two creation and two annihilation operators. There could be higher order of interaction terms, but we are mostly going to be talking about interaction terms where two particles come and interact and they exchange their spin, momentum, etc., and they go on as two different particles. There could be production of particles as a result of scattering, but let us not talk about that immediately. We will sort of only be constrained with each of these h primes having two creation and two annihilation operators. So, h prime has a c dagger c and a c dagger c with momentum and spin indices as a case requires. So, the expectation value of the time ordered product is taken with respect to the non-interacting ground state. This is what we have learned. It is actually the ground state of the many body system, but then we learned how to construct non-interacting ground state from an interacting many body ground state, and we have shown that there is a phase factor that comes which connects the many body ground state as well to that of the non-interacting ground state, and properly done we can simply take the time ordered product to be taken between, or the expectation to be taken between the non-interacting ground states. All the operators, point number 5, all the operators are written in the interaction representation. This is important because this Green's function is fully in the interaction representation, in which both the wave functions and the operators, they carry the time dependence. Somehow it is only important for us that the operators carry the time dependence, but nevertheless we should write those operators, the creation and the annihilation operators, to be in the interaction representation. In fact, the difference between the interaction representation and the Heisenberg representation is that the Heisenberg representation has similar time evolution as that of the non-interacting system for the interaction representation. So, now the non-interacting, so the interacting Green's functions are written in terms of the products of non-interacting Green's function and the number operators. This is done by doing a normal ordered product, and each of the, or rather the interacting or the full Green's function is split up into several of the non-interacting Green's functions and or the number operators, and then of course the interaction vertex. What we mean by that is what we are going to come next. The interaction vertex will appear, and or the strength of the interaction will appear, and the full Green's function will contain information about the nature of the interaction vertex or the strength of the interaction. Such products are most conveniently computed using Feynman diagrams. So, we are next going to discuss Feynman diagrams, but before that let us write down one example of a Green's function and see that what it means or how it can be split up, decomposed into the non-interacting Green's function. So, we start with an example, and let us write down apart without those factors of minus I etcetera, we will simply write down a time ordered product, and this means this left angular bracket means that it is taking with respect to phi naught. One can write it also explicitly, but it is understood. So, it is a CKT, CK1 dagger T1, CK2 dagger T1 and CK 2 plus Q plus CK 2 plus Q T1 and CK1 minus Q T1 and CK dagger T prime, and so this is the one that we are going to have. So, let us just write it as so there will be nothing here and there will be nothing here, but as I said, the angular brackets denote that we are taking the expectation with respect to the non-interacting Green's function. Now, what we have done is that we have simply written this as the this is the H prime T1. So, we have written down a first order Green's function. Okay. Containing one H prime, one annihilation operator here and a creation operator here. So, that is our that is the term that we need to calculate. So, let us write down or rather number these operators, so that we can take the proper combination in order to write the non-interacting Green's function. And so this is 1, this is 2. Let me write a different color for that, so that this is 1, this is 2, this is 3, this is 4, this is 5, and this is 6. So, what are the combinations allowed? So, possible combinations. So, A will be A is 1, 2, 3, 4 and 5, 6. That is combination number 1. So, we can take a combination of 1 and first and second term, third and fourth term, and fifth and sixth term. Also, we can take first and third term. So, the combinations are being formed by one creation and one annihilation operator. So, 1, 3, 2, 4 and 5, 6. So, we have a third combination, which is 1, 3, 2, 5 and 4, 6. So, that is the third combination, and D to be 1, 2, 3, 4 or rather 3, 5, 1, 2, 3, 5 and 4 and 6, 4 and 6. Fifth combination is 1 and 4, 3 and 2 and 4, 1 and 6, sorry, 1 and 1 and 6, 2 and 2 and 5 and 3 and 4. So, 1 and 6, 2 and 4 say, and 3 and 5. So, this is the fifth combination, and there will be another one. There will be another one which is 1, 6 and 2, 5 and 3, 4. Okay. So, these are the 6 combinations, and the 6 combinations are coming because of we have 3 operators, 3 creation operators and 3 annihilation operators. So, there are 3 factorial combinations possible. So, all these 6 combinations for just for the first order Green's function have to be evaluated. So, let us first write down each one of them, and specifically we shall take some time and treat this as a tutorial such that you learn this decoupling and writing it writing the full Green's function, the first order Green's function as in terms of the non-interacting Green's function. So, the first term is according to the combinations prescribed 1, 2, 3, 4 and 5, 6. So, we will take a combination of CKT, CK1, T1, then CK2 dagger and CK2, and then CK1 minus K and then CK dagger. Remember that is not going to be the Green's function unless you multiply it. It is going to be a non-interacting Green's function if you multiply it with a factor of I, because the Green's function itself is defined with a factor of minus I. So, A becomes equal to T CKT and CK1 dagger T1, right. And so, this one and then it is T CK2 plus Q T1 CK2 dagger T1 and a C time ordered of CK1 minus Q T1 and CK dagger T prime, and these are the 3 combinations that I get. And so, I will have to multiply each one of them by a negative sign, and also do not forget to bring in the negative sign that comes because of the swapping of the operators, that is very important. So, setting that aside for the moment, we would write this one as delta k K1 and G0 K T minus T1. Okay. And so, just remind you that a factor of I is what we have dropped so far, but we will get it back once when we do more thorough calculations. So, this is the first term. So, your k has to be equal to k prime, that is the conservation says, and this is a G0, a 0th order Green's function, which is a function of k and t minus T1. Now, this one necessarily demands that because K2 plus Q has to become equal to K2, which means that this is necessarily a delta Q equal to 0 and a delta Q equal to 0, and now this is going to be a number operator because it is at same time, at time t equal to T1. So, it is not a propagator or a Green's function that propagates the system from some time t to some time t prime. So, it just loops back to the same time. So, we will write it with a n, and this is xi k, where xi k could be epsilon k minus mu, where epsilon k is the other single particle energies. Similarly, so this is the second term, and similarly the third term is here. So, that is again equal to delta q equal to 0 and a G 0 k 1 and T 1 minus T prime. So, this is how we have now written it the full Green's function at the first order in terms of the non-interacting Green's function G 0 and a number operator which is n of xi k and another G 0 which is there. And how to compute this is what we will see, and that is where the Feynman diagrams play a role. But before that, let us write down all the terms. The second term, so again I want to remind you that I am treating it as a tutorial. You should do each and every term by hand and satisfy yourself that this is what is coming, because this forms the basis of what we are going to do next with the Feynman diagrams. Similarly, for B we have T C K T C K 2 dagger T 1 T C K 2 plus Q T 1 C K 1 dagger T 1 and T C K 1 minus Q T 1 C K dagger T prime. So, this tells that it is equal to delta k k 2 sorry, this is delta k and k 2 not k prime, and G 0 k T minus T 1. And similarly, this one will have delta of k 1 equal to k 2 plus q, and this will be simply a G 0 and k 1, and again this will give me so this is from T 1 to T 1, which means it is a time that the time is repeated, provided I have written it correctly. Yeah, that I have written it correctly. So, this will be, but this is not at a given q equal to 0. So, this will be like G 0 and k 1, and this will be like a T 1 k 2 plus q. We will come back to this, and we will have a delta k 1 minus q is equal to k, and there is a G 0 and there is a k and there is a T 1 minus T prime. And so, these ones, so let us write down the number C. T C K T C K 2 dagger T C K 1 minus Q T 1 C K 1 dagger T 1 and T C K 2 plus Q T C K dagger T prime, and so on. So, this tells me that this is equal to delta k k 2. Again this is at the same time. So, this is equal to a number operator and a xi k, say for example, and again this is for so this is k equal to k 2, and this is for so this is actually k 1. So, this is delta k q equal to 0, and there is a number operator xi k 1, and this will be delta k k 2 plus q, and there is a Green's function which propagates k t minus t prime. So, these are the three terms there, and similarly for D we have T C K T C K 1 dagger T 1 and T C K 1 minus Q K 1 minus Q T 1 and C K 2 dagger T 1, and similarly T C K 2 plus Q T 1 and C K dagger T prime, and so on. So, this is equal to delta k 1 and G 0. Once again, to remind you that this G 0 will have to add an I. So, that without that it does not become G 0, we are writing it loosely without that factor of I. So, this is k t minus t 1 and now this is of course will have a delta k 1 minus q, which is equal to k 2. So, this is k 2 and this will give me a so just like the first one, it will give me a so it will be like a n xi k 2. Similarly, this will also be k 2. So, this will also be, let me correct it here, this was written mistakenly. So, this will be like n and xi k 1. So, similarly, it will be xi k 2 and then this will be like delta of k 2 plus q G 0 and k t 1 minus t prime. So, that is the fourth one, and similarly the fifth one can be written as there is something interesting about the fifth one which will come. So, we have a c k t and c k dagger t prime c k 2 plus q t 1 c k 1 dagger t 1 t c k 1 minus q t 1 and c k 2 dagger t 1. So, these are the three terms. This term will give me a delta k. So, this is anyway k. So, delta k k and there is nothing, but there is a G 0 which is at k to t minus t prime. Similarly, this will be k 1 to k 2 plus q, and again it will be like this k 1 and this will be like delta of k 1 or k 2 k 1 minus q and a G 0 and k 2, and this is at the same time. So, this will actually be so this will actually be a n, which is xi k 2. Anyway, so these are 5 terms, and to write down the sixth term, we have t c k t c k dagger t prime t c k 2 plus 2 t 1 c k dagger t 1 and c k 1 minus q t 1 and c k dagger t 1, and again this is equal to a G 0 k t minus t prime. There is nothing to write here. So, let me erase this part and write this one has to be written as a delta, this is k 2. So, this is equal to q equal to 0 this and a k 2, and similarly this one is also delta q equal to 0 xi k1 and so on. So, it is 3 5 3 and 5 k2 and k1 minus q. So, this is actually k2. So, this is the last one is 3 5, 3 is T1, this T1, this K2 and K1 minus K2, 3 is K2 and this K1 minus Q, this K2. Okay. So, this is K1 minus K2 equal to. So, this is anyway. So, these are the terms that are need to be written down, including the 0th order Green's functions. And now, if you write down a second order Green's function, you will have many more terms, and we can write down, and then there will be a second order Green's function will have how many terms? A second order So, how many creation and annihilation operator? 2 h prime will give me 4 4 8 4 creation operators and 4 annihilation operators, and 1 will come from the Green's function definition. So, there are 5 creation and 5 annihilation operators. So, this will contain 5 factorial terms, which means that equal to 5 into 4 into 3 into 2, which is equal to 20 into. So, it is 120 terms that will be there, a second order itself, and the third order you can understand that it will go as. So, a third order will have so 6 7. So, 7 factorial number of terms. So, the question is that how actually to compute all these terms, even if we say want to write down the first order Green's function that is containing 1 h prime, we got 6 terms, and maybe some terms are 0, we do not know as yet, but even then the non-zero terms, how to compute them, that is the question, and the computation of these terms are done by Feynman diagrams. So, this is we will introduce Feynman diagrams here. And tell you the basic features of the Feynman diagram. So, Feynman introduced this idea of representing the terms in these above discussions or above expressions by diagrams, and these diagrams are actually very very important in a number of physical processes, which are themselves, I mean, interesting scattering problems. So, the rules of the diagram. So, rule number 1 is that a solid line with an arrow pointing from smaller time t prime, which is a smaller time, to t, which is larger time, for free electron Green's function with momentum information. Okay. So basically that tells that this is like this with a t prime going towards a t, and there is a momentum information. So, this line carries a momentum p. So, the system or rather the free electron Green's function propagates the free system from a smaller time t prime to a larger prime t and corresponding to a given momentum p. So, this is written as this is equal to g 0 p t minus t prime. This is the notation for that. This is for the electron Green's function. What about the phonon or the photon Green's function? Let us just write it for the photon or phonon. So, a dashed line with no arrow for the phonon Green's function, and no arrow because phonons can move in either direction on the line, that is in time. Sometimes this so it is this line and there is a t prime to t, and similarly there is a say a q momentum. We will not put an arrow. Sometimes this is also written it with a springy line like a spring. So, this is t prime and t, it is also written like that, and it is written as d 0 q t minus t prime. So, these are the electron and the phonon non-interacting Green's function. Third, very importantly, the electron density n of psi p is shown via a loop to imply that it starts and ends at the same time. So, it just shows like this, we show it by an arrow this. So, this is p and this is time, it starts from the same time, I mean it starts from time t and comes back to the same time, and this is written as psi p. This is what we were writing earlier. Fourth, any interaction term V q is represented by a wiggly line. So, such as this. So, this is, it may carry a momentum q. So, this is the v of q, v is a function of q. It could have an energy information which means that it will be a v q omega. So, for example, we can write down one of the terms in this which had so a G 0 p v of q which comes from n int, and there is a G 0 p minus q and a G 0 p will be shown as a line, and then there is a wiggly line. So, it comes from I mean we have not written the time information, but the time is actually t 2 t minus t 1 and t 1 minus t 2 etcetera. So, these are this and so on. So, this is say p, this is p minus q, and this is again p. So, an electron was coming with momentum p and it scatters off by a potential v of q which takes away a momentum q here. So, that is why the wiggly line is represented by, wiggly line is the v q which carries a momentum. Then, so this is the leftmost side is the propagated here, the v q is by the wiggly line, and p minus q is the propagated here, and then there is a propagator there. So, the total Green's function or the total expression for the interacting Green's function at the first order is written as a G 0, and then there is a wiggly line, and then there are sort of is the propagator from p some time t to t 1, or so this is like t 2 or t prime, which we have not put it here. So, maybe t 1 and then maybe t 2 and then maybe t and so on. So, these are the way to write down this each one of those terms that we have got. And so, now rule number 5 is that at the vertex, there is a momentum and energy conservation So, what I mean by vertex is these points, that is a vertex and this is a vertex. There are energy and momentum conservation, and so what we have to do is that, so integrate over all the intermediate momenta and sum over all integrate over all so integrate over all intermediate let us not write it as momenta, as energies and sum over all intermediate. So, basically it is you have to integrate over all, let us not introduce this word sum and over all intermediate momentum. So, that is the rule number 5. That is rule number 5. And the rule number 6, immediately it will not be clear, but nevertheless we will put it anyway. Multiply by a factor of I to the power n, because each Green's function, to convert a line into a Green's function or each of these time ordered product into a Green's function, we need to multiply it with I. So, each of the terms will have to be multiplied with I, and hence n of those terms will have to be multiplied with I to the power n, and then we will have to also multiply it with a minus 1 whole to the power f, where f are the number of closed fermion loops. So, these are the number operators. So, if we have one number operator, then we will have to multiply it by minus 1 to the power 1. If there are two of them, then it is there will be no sign, because minus 1 whole to the power 2 it will have to be multiplied by, and so on. So, these all these rules put together from 1 to 6 as written there will help us in writing down these Green's functions, the fully interacting Green's function in terms of the non-interacting Green's function, and then by summing over all the intermediate momentum and energy, we will get the finally the interacting or fully interacting Green's function. So, let us write down at least one term. We have written down one term already. Let us write down another term, which is which was written down by us. So, example is time ordered C k t C. This is the third term in the example that we have done, t, and we have t C k 1 minus q t 1 and C k 1 dagger t 1 and C k 2 plus q t and C k dagger t prime. So, this term can be written as a line which will go like this from a t prime to t, and then there will be a term which is and there is an interaction term. Of course, that we are not writing it explicitly, but the h int will come with a v q here, and this so this will be here. So, this is a, because this will correspond to delta q equal to 0. So, this interaction term corresponds to v q equal to 0, and this corresponds to so this is one Green's function, taking it from some t prime to some intermediate t 1, and this another. So, this is that Green's function. So, this is that Green's function here, this is that again that Green's function which is here, and this is that term which is here. Okay. So, this is a fermionic bubble. So, there is one fermionic bubble. So, we will have to multiply it by minus 1 to the power 1, and since there are 3 such terms, we will have to multiply it by I to the power n, which is what we have prescribed, I to the power n. So, it is I to the power 3, and rather there are 2 Green's functions. So, we will have to write it with I square, and there will be a minus sign coming because of this. So, this is momentum is k here, momentum is so this does not carry any momentum. So, this is and this has momentum xi k 1, and this continues with the momentum k. So, a free particle Green's function propagates from minus t, from t prime to t 1 with a momentum k. Then there is a interaction vertex which carries no momentum, it is connected to a fermionic bubble, and then it carries on with. So, the Green's function or the propagator carries on with a momentum k from time t 1 to t. We will do more examples of Feynman diagrams, and we will in the next discussion we will try to compute them by computing the internal summing over the internal momenta and the energies we will calculate and for a specific case.